Yo guys, what's up? Welcome back. So I will be starting the data science series, the projects which I had built earlier. And today the project is about the cars dataset, and you can download the whole file of the dataset from this GitHub, or you can download it from Kaggle also. And the data file name is car dataset 2025. So I have made the you can say directories data models. So data will be include all the data sets, then pictures, models. We have typical files also, the notebooks, and the source folder contains the data ingestion, feature engineering, model trainer, pre-processing. So these kind of files, this all contains. Okay, so before in the data science, before we should start working on our model, we should first analyze what the data is, and is there any problem with the data like skewness, or there is some null values. So we need to fix those kind of things first of all before starting any data science project. So let's start by using EDA, exploratory data analysis. So first of all, we import the pandas, NumPy, and Matplotlib, and Seaborn also. Then I load the CSV file. So my data CSV file is in data folder. So I upload. So like I get from there, and from df.head, we can see the top five rows from the start. So the in the file, we have the company names, we have the car's names, engine, the battery capacity of the car, the horsepower, total speed, performance, and the car price also, and fuel types like petrol, hybrid. So these kind of fuel types we will have in our dataset. Then the seats and the torque, which is in 100 nm, which is the unit of the torque. So we can see there is some categorical data set also and some numerical data set also. And in our data set, we need to remove, because for the machine learning models, we just need the numerical values. So we need to convert the categorical values, and we need to remove the seconds, kilometer per hour, HP, these kind of stuff also. So let's start. So let's first check our null values if we have in our data set. So df dot shape will give the shape. So we have 12,000, 1,218 rows and 11 columns. And df dot info will give the information about the data which we have. So we have company names, and our null data type is object. And then we can see there are some rows where some like some things, some values are missing, especially in the torque performance and the capacity, engine capacity, battery capacity. So we need to perform some operations there to like get the values. So, and since our missing data, so see here in the torque we have just one missing, and in the performance we have six missing, and the battery capacity we have only three missing values. So because the data set is missing data is less than 1%, we can use the KNN imputation. So imputation means to fill out the null values, and specifically why we are using KNN imputation. So KNN imputation is for, you can say, if we have any suppose for any car in our data set there is no torque value, so KNN imputation will first try to locate that value or that row. Okay, and then based on some similar you can say similar cars names, engines, horsepowers, it will assign the value which other cars of similar type have. So this is how KNN imputation works here. And we can also use median imputation, but I will try to use KNN imputation here. So let's first of all check the null values. So this is the data, and you can get the whole file from the description, from the this video description, from the GitHub. Okay, so for the null data, this is the is null. This will calculate the all the rows which have the null values, and it will calculate the sum. Then we can calculate the percentage, and we create a new data frame for the missing values. And then using the heat map, we try to plot the null values. So you can see here for the performance, we have this orange or yellow type, you can say, a yellow or orange color, which represent there are some missing null values here, and rest of the heat map is totally reddish color. Okay, so there is only null values here just. And then if I go to find the categorical analysis of top 15 companies, and this code will check out like in 2025 people, how many people buys which car brand, like the top 15 most car brands which were bought in the last year. So this code will do data analysis. So we will first find out the top companies. We have the df, the data folder, data which we load, and we go to the specific company names column. We will count the values, and first 100. Okay, and then in the bar plot we will use the bar plot here, and in the x values we will give the top companies x values, and then we give index. So you can see here the top 15 car by frequency. So in 2025 most people buy Nissan, Volkswagen, Porsche, Mazda, Mitsubishi, GMC. So these kind of cars people most buy in 2025. And we can see the Bentley, the expensive, the luxury cars were least bought, but we can see the Mercedes and Audi still people bought it in like which you can afford, or people who have, you can say, higher living expense, income. So these kind of factors affects the frequency of car companies. And then we need to also see the distribution of fuel types, like people try to buy the cars which are hybrid or the petrol. So we will draw the pie chart, and we can see people try to buy mostly those cars which are of petrol. So petrol contributes to 71.5%, and diesel is 8.7%. And people also tend to choose electric cars like Tesla or EVs, especially by the China. And then people also try to choose the hybrid and petrol diesel, petrol hybrid. So these kind of distributions are also people try to bought by. And then we will see the distribution. So now we need to plot the histograms, and we need to find out the correlation. And through the histograms and through the box plot, we can find out the skewness. We can find out the outliers. Like suppose if all the cars are in the range 1 to $100,000, and the luxury cars are like $1 million, then that will be the outlier, and we need to carefully handle those outliers, because our model will think that one outlier is most important, and it will perform based on that data rather than the remaining data set. So through this model will perform poor on unseen data. So we need to handle these kind of things. So first of all, we need to clean the data. So we will check if there is any null value or none. Then we will assign the none value. And as I said earlier, we need to replace, we need to find out the exact numbers or decimal values, and we need to remove the seconds kilometer per hour in the column. So that's what this line is doing, this regular expression. And then we will convert it into float values, and for all the values which we have numerical data, we will apply this clean function, and then we will plot the histograms. So you can see the distribution of price. So you can see the distribution of HP horsepower, and you can see then there is not so much normal distribution here. So if you see in the price, there is no normal distribution we can see. So we can say there is some skewness, there are some outliers here, because you can see the data is too much on the left side. Okay, we can see the left skew here, and again we have the HP, so there is not much normal distribution, not there is no much like bell shaped. So there are some problems here in our data, and we need to fix that before training our data. So see here, so that as well, like as I said earlier, for the Ferrari or Bugatti, because these are cars which have so much high prices, and it's depend on the car brand name, then engine, then horsepower. So it depends on too many other factors, so that's why there are some outliers. And let's see like which features are correlated with each other. So let's plot the correlation matrix. So we choose the price, HPCC, speed, performance, seats. So again we can see the red values. The red values show the high correlation with other variables. So if we see the for the price is depending on the speed also, but it is more depending on the HP. So if the car had more horsepower, then we can say like specific car has more price value also. And then if we can see here for the CC, like battery capacity, so for the HP, so more horsepower, then we can expect more CC capacity. Okay, and then for the speed also, we can expect if the we can use common sense here. If there is more horsepower in the car, then there will be more speed of that car. So this is what correlation matrix shows us here. And we can draw the plots also, like how the horsepower and top speed performs over the data. So see, as the horsepower increases on the X, our speed also increases on the Y value. See, so this is the trend of our data again for the engine and the horsepower, and then for the HP and the price also. And this is the box plot, and through this we can find out the anomalies, we can find out the outliers. And I want to discuss something important here. So see the middle line in the box plot. So this shows the skewness in our data first. So if the value is in the middle, then the shape is normally bell curved, there will be no skewness. But if the line goes to the left or to the right, then there is some skewness here. So see, in the speed, as we saw earlier, it's not bell curve, there is some skewness. So it's, we can clearly see by this line also. And then we can see also the outliers in mostly in price, performance, and we have some outliers in CC, income also. And then we can also perform the Q plot, and Q plot will also tell us if the data is not like on the straight line, then it's not normally distributed. So see here, the price, the data set is going to the below the this red line. Okay, so check out my cursor. So it starts from here, then it goes down, and then it moves up. So this is not normally distributed. A perfect normally distributed graph will be all these data set, all these points will lie on this red line. So if I tell you, so see, from here and from here, that mostly the data set, the data points lie on the red line. So this is the normal distribution. But if we see overall the performance QQ plot, then again the mostly the first half and the remaining half of the data is not on the red line. So we can see it's not normal distributed again. So we have now some, you can say, some analysis of our data, and we need to know what things we need to fix. So first of all, we need to fix the outliers, we need to fix the skewness. And in the industry, we can use outliers using quantile clipping. We can use log transformation also, And similarly, we can use some techniques for the outliers also. So let's first do the data ingestion. So first of all, we will load our data file here, and from here, so we load data. We will first do the pre-processing. So in the pre-processing, I just wrote down the code. So we will first of all, from the read CSV, we will read the CSV file, then we will extract the numerical values. And again, I have applied the if condition. If there is null values or if there is lower, then we will simply add in that column just nan value. Otherwise, we will separate commas, we will separate the unit strings, the symbols, and we will remove those things, and we will just extract the exact numerical value, and we will return that. And if because we have seen the we can expect a price range of any car like 12,000 to 1,500 uh, dollars. Okay, so we need to, because our model only like it only wants one single value, one single numerical value, so we need to take the average of of that to handle our range in our data set. For the range, we will take the mean. Okay, and then we will again add the data back into the file. In the new file we will create now. So this is a clean phase. And because if we have seen earlier, there is some categorical data also, so we need to fix those things also. So we need to convert the categorical data into binary values also, so 0 or 1. So we have categorical data of company and the fuel type, so we'll strip them, and then we will create the new columns to easy to be used later in our project. So this is the column, and I just created new columns based on our data. So this will get all the seeds, and then we also applied the numerical value to seeds, because that is not numeric, or it's not a float value, it's the object. So we need to convert the object into float so our model can understand. And then we need to fill the null values also, so we can expect some null values as we seen in the CCHP speed. So we will use Canon imputer. And the reason, as I said, we are using Canon imputer because suppose if a car is missing some acceleration or some torque, and in general we can't uh, see any car have zero torque, because it's impossible. So what the Canon imputer will look, it will do like it will check all the other 5 cars with similar HP, with similar capacity and price, and then it will estimate the most, you can say, logical torque value. And to fix the skewness, I tried to implement the log transformation, but that didn't help the data much, and the skewness was not like close to 0. So then I applied again the new technique, which is quantile clipping. So quantile clipping, we give the lower limit and the upper limit, and it will skew the data no matter if there are outliers or not. It will skew the data between lower limit and upper limit. Okay, so for the price, torque, HP and capacity, it will skew all the data between lower and upper limit. So lower limit is 0.01 quantile of our data, and upper limit is 0.99 quantile of our, suppose we have price. So upper quantile is this and lower quantile is this. We will skew the data in between, and then we will apply the power transform. And here we specifically use Yeo-Johnson, and we will import the power transform from Scikit-Learn here. So for the pre-processing to remove the skewness in our data, and then we will use this standard scaler. So all our data is scaled from 0 to 1. Okay, because see, we have the categorical data and we need to do one hot encoding. So, and also we need to do the dimensionality reduction also, because we will after one hot encoding we can expect so many columns, so we need to reduce the columns also. So that's why we need to use this standard scaler also here. So speed and acceleration. We will apply the scalar there, and then we will just rerun the processing file, and then it will create the new preprocessed data.csv file here. And after all the pre-processing, now let's move to the feature engineering and PCA. So when you come here in the feature engineering part, here you will see, as I said, we need to convert the categorical data into binary column. So we will use the hot encoder. So we will import the hot encoder from scalar. We don't need to use standard scalar here because we used that earlier, and we don't need to perform it on categorical data because it's already in 0 and 1. So that's why. So we will apply the hot encoder on company and fuel type here. Then we will do the fit transform, and I am just creating the pickle file because I need to use them in our Streamlit application. So that's why I'm trying to uh, create the all files, important files also, so later we don't have any problems. So I created a new data frame for the encoded one, and for the encoded data, we have the fit transform options on the company and fuel type. Okay, we will get the get features. Okay, so encoder have built-in a column, built-in function which will get all the feature names out of the columns. So that's our encoded uh, data set now, and we will combine this all pre-processed data with our original scale data also, and the fixed data which we get after the quantile clipping to remove the skewness. And then we will just concatenate the numeric features, and after we applied the hot encoders. Okay, and we also need to use the anomaly detection. So the reason I use anomaly detection is because, let's see, for example, if the model tries to, you can say, learn from a Ferrari as if for a normal car, then it will deal with the model will get confused, and the remaining data set and the remaining, if we try to predict the remaining cars, then it will likely 99% will fail on that data set. So we need to detect the anomalies, like which have so much high prices. So we need to find out that because our independent column is y value, which is price. We need to predict those things, and then, as I said earlier, we need to apply the PCA. So PCA will reduce the number of columns. Okay, so originally, if I show you after I applied the pre-processing, if you come into the final EDF file, so first of all, initially we have 11 columns. Now after applied the hot encoding, we have 67 columns here, and these missing values. And see, after I applied the quantile clipping, we can see the normal distribution curves. So there is some sort of problem here, like in here. So if in the HP there is some problem, but this can we can work with this data, and then there is some normal distribution. We can now see exactly there is some normal distribution here. And for the outliers, see, in the box plot now, mostly this middle line is in the middle, and only we have some problem with the speed, but that's okay. We have just one feature where have we some problem, but that's okay. We can go with that. So we fix the outliers, we fix the skewness here. Okay, and so that's why, as you see, we have 67 columns. So we need to reduce the dimensions of our data set now. So that's why I use the principal component analysis, and I want to convert back data into two component, PCA1, PCA2, and PCA1 or PCA2 will now represent the company or brand name or the fuel type which we have. And again, I am just like saving the models, saving the pickle files because we need it later, and then the target fixed price also. So this target fixed price is the price which we fixed after apply all the uh, pre-processing. Okay, and then we just run this file. I already run the file, and we will get the final feature set. And in the final feature set, if we see, so this is the final feature set EDA, and we don't have any missing values. We have fixed the quantiles, we have fixed the skewness, fixed the outliers, not the quantiles here. So see, and then now we will go back to the model trainer. So in the model trainer again, we will import the pandas, then joblib. So joblib library is used to import or to save the pickle files, and then we will again matplotlib, sklearn, so these kind of things, and then we will train our model. So we will read the file. The file will be here, the final feature set, where we have applied the pre-processing, feature engineering, and then we will because our target price is target fixed price, and we will drop the is anomaly because we don't need it. Okay, and then we will split again 80% training and 20% testing, and again I will save the columns here. And for this model, for this exact problem statement, I'm using the random forest regression model because it will calculate, it will make all the trees, it will do all the calculations, and it will perform better here than the simple linear regression. And then we will make predictions. Model predict, we will calculate the R2 score, the mean absolute, mean squared, and this scored is just used to demonstrate the outputs of how our model performs. I also save the output here, and this function is used to create the plots. So the most important features we have is horsepower with 69% importance. The torque is much have importance, 14%. PCA1 and PCA2 is also have importance in predicting the price of any car. And PCA1, PCA2 represent here again the brand name or the fuel type. And the capacity also is important here. And in this file, in the abort file, you can see the Streamlit application. So first of all, we will load the load assets and the cache resource. I use this cache resource so our Streamlit applications will not halt when we try to make predictions, and it will not again and again try to load all the assets. It will just load it one time and we can use it again and again. So it will try to save the memory computation power. Okay, so we will load all the assets. So because we need the model and we need the power scaling, PCA encoding, the reason we need all these files is because we made some changes in our data, we converted our data. So we when we get the data from the user, so we don't need to tell the user like you need to you can say uh, you need to input the PCA1 value because user don't know what is PCA1. So internally we are handling all the values, and these pickle files are handling that data. So that's why we need these values. So this function will load all the load assets and it will just return. And with column 1 we have company, fuel type, horsepower. So this will be all the input and this will be the output. And for the dummy array, see, we have numpy array, we will get the values because the torque, horsepower, and the capacity, and the reason this value is 0, it represents the price because the price we are calculating. But in the power transformer, when we just try to remove the skewness, we use the price also at that time, because there are problems with the column of price. So that's why we need to give the exact data which through which we trained or through which we pre-process our data. So that's why we need to give the exact values, otherwise we will find problems, or your app or your sim application will break in production also. So this is the application, all this code, and this is the fast API, so you can deploy. Again, we need to load all the assets, then this will be the class for car input. Home, we will do the prediction based on the values which user will give here. And yeah, so this is all the files here, and now let me show you the predictions, like how the Streamlit and how the first API works. So see here, this is the Streamlit UI. We can add the company name, and uh, you will be expecting like how we get all these values. So remember, I save the train column speckle file. So from that train column speckle file, we are loading all these company names, these fuel types. So these kind of things we are getting from that thing. Okay, and let's suppose we want to buy the BMW, any BMW car, and we need the top speed of, let's say, 300, and from 0 to 100 kilometer we need in let's say 12 seconds, and we need the petrol, CNG petrol. Horsepower, we need horsepower of 450, torque of 450 horsepower, let's say we need 1000, engine capacity we need 4000, and seats we need 4, and let's estimate the price. So our model is predicting the specific car of BMW which have these features of top speed 300, horsepower 1000, engine capacity this, torque 450. It's calculating $95,000. So I think that's pretty much accurate, because our model score was 92%. And yeah, so that's the whole end-to-end project we have built. And the Docker files and all the files you will be available in the this YouTube video description, and you can check that from here. And free feel to if you have some issues, then you can open there on the on the GitHub. Or if you want to implement some more features in this project, then you can do that also using creating creating pulling request on the GitHub. So yeah, that's it for today. Have a great day. Take care. Bye bye.